So these are the equation. These three are the equation. So now we'll start the chapter projectile motion. So what is a projectile motion? Projectile motion refers to the motion of an object projected into the air at some angle. The important thing here is velocity of projection, that is the velocity with which the object is projected into the air, and the angle of projection, that is the angle which the velocity vectors make with the horizontal. So let's see this with the help of an animation. So here, as you can see, this is our projectile, which was thrown into the air with velocity u. So this is our velocity of projection. And the angle of projection is theta. So this is the angle which velocity vectors makes with the horizontal. So here we can see that we can resolve this velocity vector into two components, one along the horizontal, which will denote by ux. So ux will be equal to u cos theta, and uy will be equal to u sin theta. Now let's try to find out the equation of the path of projectile. So as we have seen, the velocity of projectile can be resolved in two components along horizontal and vertical direction. So the component of velocity in the horizontal direction is ux, which is equal to u cos theta, and in the vertical direction it's uy, which is equal to u sin theta. Now let's see what acceleration is acting upon this projectile. So there is only one acceleration, which is gravitational acceleration, that is g, which is acting upon the projectile, and it is in the negative y direction. So the acceleration in the x direction is 0, and in the acceleration along vertical direction is minus g. So in time t, projectile will travel a distance x along the horizontal direction, and which will be given by ut cos theta, where t is equal to time. Similarly, in the vertical direction, the distance traveled in time t will be given by u is equal to ut sin theta minus half gt square. So these are the two equation 1 and equation 2. Now from equation 1 we can write t is equal to x by u cos theta, and we can put this value of t in equation 2. So we can write y is equal to u sin theta into t minus half gt square. We can put the value of t as u cos x by u cos theta, so y will be equal to u sin theta into x by u cos theta minus half g x by u cos theta whole square. So finally we get the following equation: y is equal to x tan theta minus half g by u square sec square theta into x square, and this is the equation of a parabola. So the path of the projectile is a parabola. We have denoted the equation of the path as equation 3. Now equation 3 can also be represented as y is equal to bx plus cx square, where b is equal to tan theta and c is equal to g by 2e square sec square theta. So this is another way of representing the equation of the path of a projectile. Now let's calculate the time of flight of projectile. Once projected, the projectile will come back on the surface after t seconds, where t is the total time of flight. So let's calculate this time of flight. As you can see from here, after time t, which is time of flight, the projectile is once again on the ground. So to calculate this time of flight, we'll make use of the following formula. We know that the displacement along y direction, that is along vertical direction, is given as ut sine theta minus half gt square. Now as you can see, the displacement along y direction will be 0 at time t is equal to 0, because if you put t is equal to 0 in this formula, you will get y is equal to u sine theta into 0 minus half g into 0 square, which is equal to 0. So at time t is equal to 0, the displacement along y direction is 0, which can be seen from here. At time t is equal to 0, the projectile is here. This is our projectile. At t is equal to 0. Also y will be 0 once again when the projectile touches the ground. So if you put y is equal to 0 in this equation, we'll get 0 is equal to ut sine theta minus half gt square, or ut sine theta is equal to half gt square, or t is equal to 2u sine theta by g. So after this time, that is 2u sine theta by g, the displacement along y direction is again 0. So this is our time of flight, that is t is equal to 2u sine theta by g. Now let's calculate the range of the projectile. Range of the projectile is defined as the horizontal displacement after the end of the flight. So to calculate this, let's see the animation again. So as you can see from here, let's say that projectile starts at point P, which is the origin, and after the end of the flight, it is at point Q. So this PQ would be the range of the projectile. So in order to calculate the range of the projectile, we need to find out the horizontal displacement in time t. So to find that displacement, that is x, we need the velocity in horizontal direction, which is u cos theta, and the time of flight, which is 2u sine theta by g. So the range will be 2u square sine theta cos theta by g Now 2 sin theta cos theta is equal to sin 2 theta, so we have range is equal to u square sin 2 theta by g. So this is the horizontal displacement of the projectile at the end of the flight. Now let's calculate the maximum height of the projectile while in motion. The maximum height of the projectile occurs at time t is equal to capital T by 2, where capital T is time of flight. Now let's see this graphically. So as we know, the path of the projectile is a parabola, and the maximum height occurs at this point, which is symmetrically located. The parabola is symmetrical about this line, and this is the maximum height, which we'll denote by capital H. So from the symmetry of the figure, it is clear that the maximum height will occur at time t is equal to capital T by 2, where capital T is total time of flight. So now to calculate the maximum height, we need to find the y displacement at time t is equal to t by 2. So the displacement along y-axis is given as uyt minus half gt square, where ui is the velocity along y direction, which is equal to u sin theta t. So we have y is equal to u sin theta t minus half gt square. Now we already know that capital T, that is time of flight, is 2u sin theta by g. So t by 2 would be u sin theta by g. So putting this value of t, that is putting t as u sin theta by g, will get y is equal to u sin theta into u sin theta by g minus half g. T square would be u square sin square theta by g, or y is equal to u square sin square theta by 2g. So this is the formula for the maximum height of a projectile, which is projected with a velocity u at an angle of projection theta. Now we'll try to find out what is the maximum range for a given velocity u. As we have seen earlier, the range of a projectile is given by r is equal to u square sin 2 theta by g, where u is velocity of projectile and theta is angle of projection. So from this expression, it is clear that for a given initial velocity u, the value of r will be maximum when sin 2 theta is maximum. As we know that the maximum value of sin 2 theta is 1, so when this occurs, the maximum range will be given as u square sin 2 theta by g, where when we put the value of sin 2 theta as 1, we'll get maximum range r max as u square by g. Also, when sin 2 theta is 1, it means that 2 theta is 90 degree, so theta would be 45 degree. So for any given initial velocity u, r will be maximum when the angle of projection theta is 45 degree. Now we will see what is the maximum height that a projectile can attain while in motion. As we have already seen, the expression for maximum height was h is equal to u square sin square theta by 2g. Now for a given initial velocity u, h will be maximum when sin square theta is 1 or theta is equal to 90 degree. So the value of h max would be u square by 2g. Now since here the theta is 90 degrees, so the path of the projectile won't be parabolic,